To enter your bloodstream, a drug molecule must survive a chaotic, high-speed collision course through a dense biological barrier. To predict exactly how and when this happens, pharmacologists rely on a remarkably simple physical model, the two-chamber diffusion cell. This experiment tracks the movement of molecules from a donor fluid into a receiver fluid, generating a single cumulative permeation curve. This graph plots the cumulative amount of drug crossing the barrier over time. Absorption does not start instantly. There is an unmistakable delay, a shallow upward curve across the beginning of the timeline. Then the curve snaps into a rigid, straight diagonal line. What physical mechanisms are happening inside that microscopic barrier to cause this delayed onset before locking into a constant rate? By deconstructing this single curve, we can derive the mathematical laws of diffusion and isolate the exact physical variables controlling drug absorption. Picture a cross-section of the diffusion cell. A biological membrane sits completely empty, separating a concentrated drug solution from a clear receiver fluid. The first curved section of this graph represents the non-steady state. It directly maps to the moment a drug is first administered to a patient. Molecules leave the donor solution and begin to force their way into the barrier, slowly saturating the empty spaces inside the lipid matrix. During this phase, there is a massive physical imbalance. Far more molecules are entering the front of the membrane than are making it out the other side. Because the input outpaces the output, the actual concentration of the drug inside the barrier is actively rising as the seconds tick by. This changing environment is mathematically modeled by Fick's second law of diffusion. The law uses a partial differential equation. dC over dt equals d times the second derivative of concentration with respect to distance. The crucial takeaway here is that dC over dt, the rate at which concentration changes over time, is a non-zero value. The internal state is constantly in flux. That ongoing accumulation inside the barrier is the literal cause of the shallow, curved delay we see on our experimental graph. Now look at the second half of this data. The initial curve disappears, replaced by a rigid, straight line. This structural shift marks the exact moment the biological membrane becomes completely saturated with the drug. The physical imbalance is gone. For every molecule pushing into the membrane from the donor side, exactly one exits into the receiver. Because the input perfectly matches the output, the internal concentration gradient across the barrier stops shifting and locks into a constant state. Mathematically, this means the derivative of concentration with respect to time drops entirely to zero. With the environment stabilized, the system is now governed by Fick's first law. This law calculates J, or flux, the constant, steady rate at which molecules diffuse through a given area. That constant rate of molecular traffic perfectly mirrors the constant linear slope of our graph. Achieving this steady state is the ultimate goal of drug delivery. It guarantees a predictable, unbroken rate of biological absorption. But applying Fick's first law presents a severe experimental roadblock. To calculate flux, the equation requires us to know the concentration gradient inside the membrane itself. In a lab, we can easily sample the bulk fluid to find the concentration in the donor side, C1, and the receiver side, C2. However, the values Fick's law needs are C'1 and C'2, the microscopic boundary layers located directly inside the barrier faces. These are physically impossible to measure. To solve the math, we need a bridge to translate the measurable bulk fluid into those unmeasurable internal boundaries. That bridge is the partition coefficient, or K. The partition coefficient measures a specific drug's chemical preference to distribute itself into lipids, like fats, rather than staying in water. By integrating the partition coefficient along with the membrane's physical thickness, H, we can algebraically substitute out the unknown internal variables. The variables collapse into a single term, P, the permeability coefficient. This is an absolute measure of a drug's ability to cross a specific barrier. By mathematically combining fundamental physical constants like diffusion mobility and lipid solubility, we bypass our lab limitations to directly quantify biological permeability. There is, however, a strict boundary to everything we've just discussed. Fick's laws strictly and only govern passive diffusion. Passive diffusion is a downhill process driven purely by the concentration gradient, requiring zero energy expenditure from the cell. Look at the mechanism shown in this diagram. Some molecules have to move uphill against the gradient, completely breaking Fick's mathematical model. This is active transport. It relies on carrier proteins and requires a direct input of cellular energy, or ATP, to function. Drugs engineered to mimic endogenous nutrients, like specific amino acids or pyrimidines, intentionally hijack these active biological pumps to enter the bloodstream. While Fick's laws perfectly model spontaneous physical motion, active transport requires biological machinery to forcefully bypass natural equilibrium. Let's return to the completed permeation graph from our experiment. This single output bridges complex differential equations with real-world pharmaceutical engineering. By taking the steady-state line and extrapolating it backwards to intercept the x-axis, we extract lag time, or TL. This is the time required for a drug to begin a constant rate of systemic absorption. The slope of that line represents the permeability coefficient. To change the angle of this slope, to speed up or slow down delivery, pharmacologists must physically alter the drug molecule. Making the molecule smaller increases its diffusion coefficient, while increasing its lipid solubility boosts its partition coefficient. Either edit steepens the curve. By decoding the geometry of the permeation curve, bioengineers gain the mathematical blueprint required to design highly targeted, perfectly timed drug delivery systems.